Imagine a world not too far from today, 2025. You step into your car, ready for your morning commute. But instead of gripping the steering wheel, you sip your morning chai. You might catch up on emails, or perhaps gaze at the cosmos through a learning app. The car itself, it does all the driving. This is not some distant science fiction story, my friends. This is the promise of self-driving cars, a technology that is unfolding right before our very eyes. It is a dream humanity has cherished for decades, the dream of intelligent machines navigating our bustling world. This dream is rapidly turning into a tangible reality. Think about it. Our cities could be transformed, roads could become safer, with fewer accidents caused by human error. Traffic jams, those daily banes of our existence, could ease significantly. We could reclaim countless hours lost in transit, using that time for work, for leisure, or for simply connecting with loved ones. The very fabric of our daily lives, our urban landscapes, and our economy could see a monumental shift. It is a revolution in personal mobility, a leap as significant as the invention of the automobile itself. This is truly a fascinating time to be alive, but how does this marvel of engineering actually work? How can a car, a machine of metal and circuits, pilot itself through complex city streets? How can it navigate the unpredictable chaos of human drivers, pedestrians, and unexpected obstacles? It is not magic, though it might sometimes feel like it. It is the culmination of decades of research and development. It is a symphony of sophisticated sensors, powerful computers, and incredibly smart software. These cars are equipped with senses far beyond our own human capabilities, all working together. In this exploration, we will embark on a journey. We will delve into the intricate world of autonomous vehicle technology. We will uncover the secrets behind how these cars see and perceive their surroundings with such astonishing clarity. We will look at the different types of electronic eyes and ears they use. We will understand how they make sense of the vast universe of data they collect every single second. So, buckle up, as we explore the fascinating senses of the self-driving car. It is a journey into the heart of innovation. The most familiar type of sensor on a self-driving car is the camera. These cameras act much like our own human eyes. They are designed to capture visual information from the world around the car. These cameras can see colors, shapes, and various details on the road ahead. They are essentially digital eyes, constantly observing and recording. Just as our eyes provide us with a rich, detailed view of our environment, cameras offer a similar visual input to the car's computer brain. They are a fundamental part of the car's perception system, providing a baseline understanding of the visual scene. Self-driving cars typically do not rely on just one camera. Oh no, that would be like trying to see the world with one eye closed. Instead, they are often equipped with a whole array of cameras. Some face forward, watching the road far ahead and nearby. Others are positioned to look sideways, covering the lanes next to the car. And of course, some look backward, monitoring what is happening behind. This multi-camera setup provides a comprehensive 360-degree view of the car's immediate surroundings. It is like having eyes all around your head, ensuring no blind spots. What do these cameras help the car see? They are crucial for identifying and interpreting many important visual cues. For instance, cameras can read road signs like speed limits or stop signs. They can detect the color of traffic lights, red, yellow, or green. They're also very good at spotting pedestrians, cyclists, and other vehicles on the road. This visual information is vital for understanding the rules of the road and the behavior of other road users. The car learns to recognize these patterns just as we do. However, cameras, much like our own eyes, have their limitations. Their performance can be affected by challenging environmental conditions. Think about driving in heavy rain, dense fog, or a sudden dust storm. Visibility can be significantly reduced for cameras in such situations. Similarly, driving in very low light conditions, like on a poorly lit road at night, can be difficult for cameras alone. They might struggle to see details clearly, which is why other sensors are also needed to complement their vision. These challenges are areas of active research and development. Now let us talk about a truly fascinating piece of technology called LiDAR. The name LiDAR stands for Light Detection and Ranging. It is a remarkable sensor that works by using laser beams to map the environment. You can think of it a bit like how a bat uses echolocation to navigate in the dark. But instead of sound waves, LiDAR uses pulses of light. These are usually infrared lasers, invisible to the human eye, but incredibly effective for the car's perception system. It's a very clever way to build a picture of the world. A typical LiDAR sensor, often seen as a spinning cylinder on the roof of a self-driving car, rotates rapidly. As it spins, it sends out millions of tiny laser pulses every second in all directions. These pulses of light travel outwards, and when they hit an object, another car, a tree, a pedestrian, or the road surface itself, they bounce back. The LiDAR sensor then detects these reflected light pulses. It is constantly sending and receiving these light signals, building up a detailed map. This process happens incredibly fast, many times per second. The magic of LiDAR lies in its precision. By measuring the exact time it takes for each laser pulse to travel out, hit an object and return, the system can calculate the distance to that object with remarkable accuracy. Because it sends out so many beams in so many directions, it creates what is called a point cloud. This is essentially a three-dimensional map of all the surrounding objects, made up of millions of individual data points. It gives the car a very detailed three-dimensional understanding of its environment. It's like creating a high-definition three-dimensional model of the world in real time. LiDAR systems offer several significant advantages. They can see very well in the dark, as they provide their own light source. Their accuracy in measuring distances and creating three-dimensional maps is exceptional. This helps the car to understand the shape and position of objects with great confidence. However, LiDAR also has its challenges. High-quality LiDAR units can be quite expensive, adding to the overall cost of the car. Moreover, their performance can sometimes be affected by very heavy rain, dense fog, or snow, as the light pulses can be scattered by these atmospheric particles. Beyond cameras and LiDAR, self-driving cars also rely on another crucial sensor: radar. Radar is a technology that many of us are familiar with. It has been used for decades in aviation and maritime navigation. The word radar stands for radio detection and ranging. Unlike LiDAR, which uses light waves, radar employs radio waves to detect objects and measure their distance and speed. This difference in the type of wave used gives radar some unique and very useful capabilities for autonomous driving. It is a trusty workhorse in the sensor suite. One of the biggest advantages of radar is its robustness in adverse weather conditions. Radio waves have longer wavelengths compared to light waves. This means they can penetrate through atmospheric obstructions like rain, snow, fog, and even dust much more effectively than light. So, when cameras might be struggling due to poor visibility and LiDAR might be affected by scattering, radar can often continue to see clearly. This all-weather capability makes radar an indispensable sensor for ensuring reliable operation in diverse environmental conditions. It provides a safety net when other sensors are challenged. Radar systems are excellent at detecting other vehicles and metallic objects. They can accurately measure the distance to these objects and, very importantly, their relative speed. This information is critical for functions like adaptive cruise control, where the car automatically maintains a safe distance from the vehicle ahead. Radar can track multiple targets simultaneously, providing the car's AI with continuous updates on the movement of surrounding traffic. It is particularly good at seeing far down the road, providing early warnings of vehicles ahead, even those partially obscured. However, radar also has its limitations. Compared to LiDAR, radar generally has a lower resolution. This means it might not be able to provide as detailed a picture of an object's shape or texture. For example, radar can tell you there is an object ahead and how fast it is moving, but it might struggle to distinguish between a car and a large cardboard box with the same certainty as LiDAR or a camera. It sees broader shapes rather than fine details. That is why self-driving cars use a combination of sensors, each playing to its strengths. Section 5. The Close Quarters Specialist Ultrasonic Sensors. Let us now consider the sensors that help self-driving cars navigate in very close quarters. These are called ultrasonic sensors. Think about when you are trying to park your car in a tight spot. You might rely on the beeping sounds from your car's parking assist system. Those beeps are often generated by ultrasonic sensors. These sensors work on a principle similar to radar and LiDAR, but instead of light or radio waves, they use sound waves. These are high-frequency sound waves, typically above the range of human hearing. Ultrasonic sensors emit short pulses of these sound waves. When these sound waves encounter an object like another car, a wall, or a curb, they bounce back towards the sensor. The sensor then detects this echo. By measuring the time it takes for the sound wave to travel to the object and return, the system can calculate the distance to that object. It is a relatively simple yet effective technology for detecting obstacles at short ranges. They are the car's close-range eyes and ears, constantly listening for nearby objects. These sensors are particularly excellent for low-speed maneuvers and detecting objects in the immediate vicinity of the car. They are commonly found in the bumpers of vehicles, both at the front and the rear. Their primary role is to help with tasks like parking, by alerting the system to nearby obstacles that might be hard to see. They can detect curbs, posts, other vehicles, and even pedestrians who are very close to the car. This makes them invaluable for preventing low-speed bumps and scrapes in tight urban environments or crowded parking lots. While ultrasonic sensors are very useful for short-range detection, they are not designed for long-range sensing. Their effective range is typically limited to a few meters. Also, the level of detail they provide about an object is quite low. They primarily tell you that something is there and how far away it is. However, they are relatively inexpensive, durable, and consume very little power. This makes them a cost-effective solution for providing crucial close-range awareness, perfectly complementing the capabilities of cameras, LiDAR, and radar in a comprehensive sensor suite. Section 6. The brain behind the wheel: AI and sensor data processing. So we have all these amazing sensors: cameras, LiDAR, radar, and ultrasonic sensors. Each one is constantly collecting a stream of data about the car's surroundings. We are talking about an enormous amount of information, truly vast datasets. Imagine terabytes of data being generated every single hour the car is driving. This data, in its raw form, is just a flood of numbers, pixels, and signals. It needs to be interpreted, it needs to be understood. This is where the real intelligence of a self-driving car comes into play: artificial intelligence, or AI. The AI acts as the car's central processing unit, its brain. It takes all the raw data pouring in from the different sensors and works to make sense of it. This involves highly complex algorithms and sophisticated software. These AI systems are typically based on machine learning, and more specifically, deep learning. This means the AI has been trained on massive amounts of driving data. It has learned to recognize patterns, identify objects, and understand different road scenarios, much like a human learns from experience, but on a vastly accelerated scale. The AI performs several critical tasks. First, it fuses the data from all the different sensors. For example, the camera might see a shape, LiDAR might confirm its distance and three-dimensional form, and radar might confirm its speed. The AI combines these inputs to get a richer, more reliable understanding than any single sensor could provide. Then it uses object recognition algorithms to identify what those shapes and forms are. Is it a car, a pedestrian, a bicycle, a traffic cone, or a stray dog? It classifies and tracks these objects continuously. Once the AI has built a comprehensive understanding of the current environment, where the car is, what is around it, and how things are moving, it then needs to make decisions. This is the driving policy part of the AI. Based on its understanding of the scene, its destination, and the rules of the road, the AI decides what action to take. Should it accelerate, brake, change lanes, or turn? These decisions are made many times per second, allowing the car to react smoothly and safely to the ever-changing conditions on the road. Companies like Waymo and Cruise invest heavily in refining these AI brains. Section 7. Knowing where to go: GPS and high-definition maps. A self-driving car not only needs to see its immediate surroundings, but it also needs to know where it is in the broader world and where it is going. For this, it relies on two key technologies: the Global Positioning System, GPS, and highly detailed digital maps. GPS is a familiar technology to most of us. It is the system that allows your smartphone to show your location on a map and provide directions. Self-driving cars use a more advanced and precise version of GPS. The GPS receiver in the car communicates with a network of satellites orbiting the Earth. By receiving signals from multiple satellites, the car can calculate its geographical coordinates, its latitude, longitude, and even altitude, with a good degree of accuracy. However, standard GPS can sometimes have an error margin of a few meters. For a self-driving car that needs to know exactly which lane it is in, this is not precise enough. Therefore, autonomous vehicles often use enhanced GPS systems, sometimes augmented by other positioning techniques, to achieve centimeter-level accuracy. Complementing the GPS are high-definition HD maps. These are not your average digital maps that you use for navigation. HD maps are incredibly detailed, three-dimensional representations of the road network. They contain a wealth of information, far beyond just street names and routes. These maps include precise details about lane markings, curb locations, the exact position of traffic lights and signs, speed limits, road curvature, and even the slope of the road. They are created by specialized mapping vehicles equipped with LiDAR and cameras, and are accurate down to a few centimeters. These HD maps serve as a crucial reference for the self-driving car. By comparing what its sensors are seeing in real time with the information stored in the HD map, the car can pinpoint its location with extreme precision. This process is called localization. The HD map also helps the AI to anticipate the road ahead. For example, it knows if a sharp curve is coming up, or if there is a stop sign hidden by a tree, allowing the car to prepare its actions in advance. This combination of precise GPS and rich HD maps is fundamental for safe and efficient navigation. Section 8. Overcoming hurdles, challenges, and rigorous testing. While the technology behind self-driving cars is truly astounding, and progress is being made at a rapid pace, it is important to acknowledge that there are still significant challenges to overcome. Perfecting autonomous driving for all possible conditions and scenarios is an incredibly complex undertaking. The real world is messy and unpredictable, and creating a system that can handle every eventuality with complete safety and reliability is a monumental task for engineers and scientists. These are not simple problems to solve, requiring immense innovation. One of the major challenges, as we have touched upon, is dealing with adverse weather conditions. While sensors like radar help, extremely heavy rain, dense fog, blizzards, or even layers of snow covering road markings can still pose difficulties for the current generation of sensors and AI systems. Another significant hurdle is handling edge cases, rare and unexpected events on the road. This could be anything from unusual construction zones, erratic behavior by human drivers or pedestrians, or debris suddenly appearing on the roadway. The AI must be robust enough to react safely to things it may not have encountered before. Then, there are the ethical dilemmas. Imagine a situation where an accident is unavoidable. How should the car be programmed to react? Should it prioritize the safety of its passengers or the safety of pedestrians, if a choice has to be made? These are complex ethical questions that society, not just engineers, needs to grapple with. Companies like Tesla, with its autopilot system, and dedicated autonomous vehicle developers like Waymo, from Google, and Cruise, a subsidiary of General Motors, are all working intensely to address these technical and ethical challenges through continuous research and development. To ensure safety and reliability, self-driving cars undergo incredibly rigorous and extensive testing. This testing happens in multiple phases. It starts with countless hours of virtual testing in sophisticated computer simulations, where various scenarios can be run safely and repeatedly. Then, testing moves to closed tracks and proving grounds, where cars are put through their paces in controlled environments. Finally, cars are tested on public roads, initially with highly trained safety drivers behind the wheel, ready to take over if needed. This exhaustive testing is crucial for building confidence in the technology. Section 9. The Road Ahead. Future of Autonomous Driving. The journey towards fully autonomous vehicles is an ongoing one, but the destination promises a profound transformation in how we live, work, and move. The future of driving, as envisioned by this technology, is not just about convenience. It is about creating a safer, more efficient, and more accessible transportation ecosystem for everyone. Self-driving cars are poised to become a cornerstone of future smart cities, integrating seamlessly with other forms of transport and urban infrastructure. The potential benefits are truly vast and inspiring. Perhaps the most significant promise of autonomous driving is a dramatic reduction in road accidents. A very large percentage of traffic collisions today are caused by human error, things like distraction, fatigue, speeding, or impaired driving. AI-powered cars, with their constant vigilance, 360-degree awareness, and rapid reaction times, have the potential to be far safer drivers than humans. They do not get tired, they do not get distracted by a text message, and they always obey traffic laws. This could save millions of lives and prevent countless injuries globally each year. Beyond safety, imagine the gift of time. Commutes, which are often stressful and unproductive, could be transformed into periods of relaxation, work, or entertainment. Traffic flow could be optimized, reducing congestion and saving fuel, which in turn benefits the environment. Furthermore, self-driving cars could provide unprecedented mobility and independence for people who are currently unable to drive, such as the elderly or individuals with disabilities. This enhanced accessibility can lead to greater social inclusion and improved quality of life for many. The road to a fully autonomous future is still being paved. There are technical hurdles to clear, regulatory frameworks to establish, and public acceptance to build. However, the pace of innovation is relentless. Companies around the world are investing billions, and brilliant minds are dedicated to solving these challenges. What once seemed like a distant dream is steadily moving closer to becoming an everyday reality. One day, perhaps sooner than we think, we will simply tell our cars where to go, and they will take us there, marking a truly cosmic shift in our relationship with machines and mobility.